This video is about simple machines. Basically, what simple machines do are they change how much force or the direction that a force is being applied. So, examples of simple machines are going to be levers, pulleys, inclined planes, what we normally call a ramp, a wheel and axle, screw, and a wedge. So, in all these cases, basically we've got a force that's being applied, and then we get a change in either how much force we get out or we get a change in directions. Normally, when we think about a pulley you pull downward and it lifts the other side up. But we can have pulleys where we have multiple pulleys connected together, where you get more force pulling up than you get pulling down. The important thing about simple machines is that simple machines do absolutely no extra work. Energy is always conserved. So, although we're getting more force out, it's going to be applied over a smaller distance, proportionately smaller, so that the work done is exactly the same as the work going in, if not less. If we talk about a situation like a lever here, this is a first class lever. The triangle represents the fulcrum. Triangle represents the fulcrum. We've got 100 Newton weight on one end, and then we've got an input force on the other end. So if we push this end down, this end will come up, but it's not going to come up as far. Since this end is 5 times longer, this end will come up 1/5 as far. Now, when we talk about simple machines, we usually describe them by using two terms. Their ideal mechanical advantage, which is basically the best case scenario for how much more force you would get out. The ideal mechanical advantage acts like a multiplier. If it's 2, you get twice as much force out. If it's 3, you get 3 times as much force out. The way to calculate that is by the input force over the output force. Now, this is completely theoretical. So the ideal mechanical advantage is not what you're actually going to get out. This one here is 5 times longer. So to calculate the IMA for this one, this would be an IMA of, well, my input distance is 5 over 1. So that would be just 5. So if I needed to lift this end up, I could do so by applying a force of 20 newtons here. But that implies that this bar is not going to bend at all. It has no mass. There's no energy being lost or converted into heat or something like that. So there's no friction between it and the fulcrum here. The other type of mechanical advantage is the actual mechanical advantage. So this is how much force we really get out when we apply a force in. So let's say it takes me 25 newtons to lift this 100 Newton box. That would mean my output force would be my output force would be 100, and my input force would be 25. So I would get a total mechanical advantage of 4. Your mechanical advantage at best is going to be the same as the ideal mechanical advantage. Most of the time, 99% of the time, it's going to be worse. Now, if we were doing a ramp, so in the situation of a ramp, we apply our input force like this over our input distance. The output distance is how far up the ramp it gets pushed. And then the output force would be basically the weight of this box. So if when we push something up a ramp, we're doing that in order to raise it up some certain height. So if I just like stood here and lifted it up instead of using the ramp, I'd have to do the same amount of work, but I would have to apply more force to get it to move over a shorter distance. Okay?